Okay, so percent composition. What is the percent carbon in carbon dioxide, Fred?
Um, we take the molar mass of carbon dioxide. I can't remember. What is that?
Molar mass of carbon dioxide?
Yeah.
So let's see, there's two oxygens, that's 16, right? And then one carbon.
Okay, so 44.
Yeah,
Okay, so we take 44, and 12 divided by 44 should be the percent times 100. Should be the percent carbon.
that's right. Very good. So 12 divided by 44, that's our percent carbon times 100% carbon. And then what?
The 32 divided by 44 would be the percent oxygen.
Very good. Let's see. So here's another one. A sample was analyzed and found to contain that many grams of nitrogen and oxygen. How do you find the percent composition of this compound?
Well, we haven't done one like this, but I think it's pretty straightforward. It's just total mass is going to be the sum, and then the individuals are going to be those values given.
Yeah, that's right. So if we have 0.1417 grams of nitrogen, and we're going to put that over the grams total, right?
Yeah.
And then grams of oxygen over the grams total as well. And we got 0.4045 grams oxygen over grams total. And then times by 100 to get from the fraction to the percentage, or out of 100. Okay, so what is the grams total?
0.1417.
Plus what?
0.4045.
4045, like that?
Yeah. So 0.5462.
0.5462, 0.5462. So 0.1417 divided by 0.05462. Whoops, try that again. I just had the zero in there. So it looks like 25.6%, 25.9%. 25.9% nitrogen, and 0.4045 divided by 0.5462, 74.1% oxygen.
Okay, looks good.
Good. How about this way of thinking about percentage of material? Remember this one from before this chemistry class? You did, or sometimes when you want to determine how many problems you missed on an exam, for example, out of 100, I got 23.5%. How many questions did I get right? Right? Remember that business?
What do you mean?
Well, so we have 35.5 grams of a sample. Right? There it is. And 23.5% of it is silicon, and I would like to know the mass of the silicon in that sample. If this was 100 grams, then this would be 23.5 grams. But if it's 35.5 grams, what you have to do is say the fraction is then the fraction is 0.235, and multiply that times the 35.5. Okay, so our 35.5 times 0.235 gives us our our mass of the silicon. Okay, remember how to do that from math class?
Yeah, I remember that.
Okay, good. If you don't, go through that and review it again. All right, so empirical formula relates to the molecular formula. We've talked about molecular formula, chemical formulas, but the empirical formula is the simplest whole number ratio for that molecular formula. Let's just do a couple of examples here. First one here is glucose, C6H12O6. That's the molecular formula, but the empirical formula is this simplified, right? And you can see that all these numbers divided by 6 gives us our empirical formula. Here's an example, a compound, hydrogen peroxide. We've talked a little bit about that one. If I want to give its empirical formula, what do I do?
Just divide by 2.
Very good. So HO is the empirical formula. This is the molecular formula, and that is the empirical formula. Okay, good. So C6H12.
Divide by 6, so CH2.
Very good. CH2. This is the what? Which one is this one here?
That's the molecular formula.
And this one is the empirical formula.
Yeah.
Okay, good. So now we can determine the empirical formula from the mass percent. All right, and we do that like we did talked about before. We're given some mass percentages. Maybe I say it's 60% hydrogen, 40% oxygen, for example, right? And I could say if I have a 100-gram sample of this material, then those percentages can be thought of grams, 60 grams of hydrogen, 40 grams of oxygen. And then those masses, I can convert those to moles, and then I can get the molar ratio, and that molar ratio is the empirical formula, right? The empirical formula, all chemical formulas are molar ratios. So we're going to follow that pattern. So if I have a 2.012 gram sample of compound that contains that much nitrogen, that much oxygen, we want to know its empirical formula. Okay? So the first thing we have to do is get these grams into moles, right? Because the molar ratio is the empirical formula. So do you understand what I mean when I say change the grams to moles?
Yeah, so if it's 0.522 grams of nitrogen, go to moles.
That's right. 0.522 grams of nitrogen. I can find out how many moles of nitrogen that is by converting 14 grams of nitrogen are in every 1 mole of nitrogen. So by converting the grams of nitrogen to moles of nitrogen. So now I do 0.522 divided by 14, and that's 0.0373 moles of nitrogen. I can do the same thing for the grams of oxygen, 1.490 grams of oxygen. And I can go from grams of oxygen to moles of oxygen. 1 mole of oxygen is 16 grams. That's on our periodic table, right? So 1.490 divided by 16 gives me 0.0931. That's how many moles of oxygen are represented by that many grams of oxygen. So now I have these moles of these different materials, and I can convert that into an empirical formula. All right? I can identify what the empirical formula is by saying my compound is N 0.0373, O 0.0931. Okay? Did I do that one right? 0.0931. Yeah. So this isn't a whole number ratio, though, is it? Do you remember how we get to a whole number ratio?
Just divide by the smallest one.
Yeah, because what that does is when I divide by the smallest one, 373, 0.0373, that's going to force one of these to 1, right? And then this one here, let's see what that one does. It's my 0.0931 divided by the 0.0373, and then I get O 2.50. Is that a whole number ratio?
Not quite, but now you can just multiply both by 2 because the oxygen will then become a whole number.
Okay, so we can see that that's half of 5, and if we multiply that by 2, we have to multiply this by 2 as well, but then that gives us our whole number ratio. So from this information up here, the mass of these different compounds, we identified the moles of each of them, and the molar ratio, we simplified into a whole number ratio, and so that becomes the empirical formula for that compound. Okay, good job, Fred. So, um, there is this multiplier that exists between the empirical formula and the molecular formula for compounds. All right. N2O5 might be the molecular formula, but it might be an empirical formula. We can't tell simply by the information that's provided. What kind of if this was an empirical formula, what's an example of the molecular formula that this might be an empirical formula for?
Well, empirical formulas can be molecular formulas as well.
That's right. It could be N2O5. What other molecular formulas could it be?
You mean like in 4010?
That's right. That's an example. N4O10 could be an example of a possible molecular formula. And if that was the molecular formula and this is the empirical formula, what would my multiplier be?
What do you mean?
Well, the multiplier is some value, we call it N usually, that relates the empirical mass to the molecular mass, right? Here, for glucose, for example, it was 6 because CH2O was the empirical formula and C6H12O6 was the molecular formula. So the multiplier was 6.
Well, down there would be 2 then.
That's right. The multiplier here would be 2. Okay, there are other molecular formulas that could work, right? Like N3O15, is that right?
Yeah, that works.
So there's another possible molecular formula where the multiplier here would be 3. Okay, now if we're not provided the multiplier, then we can't tell what the molecular formula is. But oftentimes, because we have instruments that can tell us what we call the molecular mass of the compound, from the molecular mass, you can compare the empirical formula and identify to the molecular mass by getting the empirical mass, and you can identify the multiplier. Okay, so let me show you how this works. Let's use, for example, H2O or H2O2. H2O2. Okay, H2O2 is a compound that has empirical formula of what? What's the empirical formula for hydrogen peroxide?
HO.
Very good, HO. So this is the molecular formula, and this is the empirical formula. And what's our multiplier there?
The multiplier between them is 2.
That's right. I need 2, and I'll write that N equals 2 here. This times 2 gives us our empirical mass. Sorry, our molecular formula. Empirical formula goes to our molecular formula. Well, the same relationship exists between what we call the empirical mass and the molecular mass. The empirical mass is just the mass of the empirical formula. So what would that be in this case?
The mass of that thing?
That's right.
Oxygen 16 and hydrogen 1?
Yeah, 17. So the empirical mass is 17. And the molecular mass here is...
34?
That's right, 34. The molecular mass was this value here, or the mass of that. And you see that the multiplier here is still 2. Okay? So we took the empirical mass, we took the molecular mass. We see that the multiplier is the same between both of them. So in a situation like this, where we say the empirical formula for this compound is NH2, and its molecular mass is 32, the empirical formula is NH2. Empirical formula is NH2. And the molecular mass is 32. So we don't know the molecular formula. The empirical mass, we haven't identified that yet. But the molecular mass, we're told, is 32. Okay? So if we're given these two, we can find these two because we know that there's a relationship between their empirical formula, the molecular formula, empirical mass, the molecular mass, by some multiplier, right? All right. And the empirical mass here can be identified how?
Oh, by taking the mass of the empirical formula.
That's right. So 14 plus 2, that's 16 there. And now I can see that the n must be what?
2.
Right, because 32 divided by 16 is 2. So this must be 2 also, right? And so then the molecular formula must be what?
That thing times 2.
Which is?
N2H4.
Very good, N2H4. So the empirical mass empirical formula, sorry, times the multiplier gives us our molecular formula. Okay? Very good. So here's a substance. Its percentages by composition. Can you determine its empirical formula?
Let's let the folks at home try it.
All right, yeah. Folks at home, give this a shot. All right, push pause. I think they did it. You want to show them how to do it now, Fred?
If it's 35, if those are the percentages, you can convert those to moles.
That's right. I can pretend like that's 35 grams of nitrogen and 5.05 grams of hydrogen and 59.96 grams of oxygen. Now, why can I do that?
You can just pretend like you have a 100-gram sample.
Very good. And I want to go from grams to what?
Moles.
So I want to go moles of nitrogen, moles of hydrogen, and moles of oxygen. Good. Grams of nitrogen can go to moles of nitrogen.
That's 14.
14 grams for every mole. This is 1, right?
Yeah, 1 gram for every mole.
1 gram of hydrogen for every 1 mole of hydrogen.
And then that's 16.
16 grams of oxygen for 1 mole of oxygen. Okay? So then I can go 35 divided by 14. .5. And then this one here is 5.05 divided by 1, which is just 5.05. And this one here is 59.96 divided by 16. That's 3.74, 3.75. Okay, so now what do I do with those values?
I'm kind of confused at this point.
Well, we converted from grams to moles. Why did we go to moles?
Well, I can't remember.
Well, what we're trying to do is we're trying to find the empirical formula, right? Which is, whoops, no carbon, which is something like this. NXHYOZ, right? We're trying to find X, Y, and Z there, those numbers in the empirical formula. Now to do that, you need to know the moles of each of these, because that's what that X, Y, and Z is. It's the molar ratio. That's why we go after the moles. So now I have those values. I can go N, there's 2.5, H, there's 5.05, and then O, there's 3.75. Okay? So I can take all of these. Is that my empirical formula?
Well, yeah, but it's not the whole number ratio.
How do I get the whole number ratio?
Divide by the smallest one.
That's right, divide by the smallest one, which is
2.5.
2.5. So nitrogen goes to 1. That's nice. 5 divided by 2.5, that's going to be, hydrogen's going to be 2. Oxygen, 3.75 divided by 2.5. What's that?
I don't know.
3.75 divided by 2.5 is 1.5.
So it's just 2?
No, because that's not really close to 2. It can be multiplied by 2, and then we get a whole number ratio. So if I do that for all my elements here, I'm going to get N2H4O3. And those will be, that's a nice whole number ratio. Okay, very good. So there we got our empirical formula from the what?
The mass percentages.
That's right, the percentage composition, which is in mass percentage. Right. Okay, good stuff.